Alright, in this video we're going to focus on physical processes, meaning phase changes, changing from solid to liquid to gas, and the amount of heat that is involved in those changes of state. So the first thing we want to look at, we have some terms that you might know, some that you might not know, that describe the phase change that's happening. So if you take a look at the diagram, obviously you know from liquid to solid is freezing, solid to liquid is melting. Liquid to gas, vaporization, gas to liquid, condensation. The other two might be new. From solid to gas is called sublimation, and that's something that dry ice does. It goes directly from the solid state to the gas phase without having to go through the liquid, and the opposite of that would be deposition. So we're going to be using those terms to represent our phase changes. Now, the phase changes that require energy, okay, if you think about what's happening, some of these phase changes, energy has to go into the object to get it to change from a solid to a liquid to a gas. And we're going to be using the term heat as the transfer of energy from an object at a higher temperature to an object at a lower temperature. Okay, so melting is a good example of a phase change that requires energy. If you have a solid and you want it to melt, you have to put energy into it to make those particles turn into a liquid. So let's look at ice. When ice is heated, the ice eventually absorbs enough energy to break the hydrogen bonds that hold the water molecules together. And then when those hydrogen bonds break, the particles move apart and the solid turns into a liquid. The ice melts into water. And the temperature at which that happens is called the melting point. Other phase changes that require energy, vaporization. If you have a liquid and you want it to turn into a gas, you're going to have to make those particles move fast enough by putting energy into them so that they can separate from each other and move around without being attracted. We call that vaporization. The term evaporation is vaporization that happens only at the surface of a liquid. So that's something that happens naturally, whereas vaporization is something that you could make happen by adding energy to a liquid. And this is going to be a new term, vapor pressure. So when you have a closed container, the liquid in that closed container, some of it's going to evaporate naturally, right? So the particles that turn into a gas, they're trapped in the container, and they're going to collide with the surface of the liquid and cause pressure on the surface of the liquid. We call that vapor pressure. And we're going to be looking at, in the next couple of chapters, how you can increase or decrease vapor pressure when you dissolve things in a liquid. And we consider the boiling point the temperature at which the vapor pressure of a liquid equals the atmospheric pressure. Sublimation is another process that requires energy to turn a solid into a gas directly. And then the opposites of all of those would be phase changes that release energy. For example, as heat flows from water into whatever the surroundings are, like the air, the particles are going to lose energy. So the freezing point is the temperature at which a liquid is converted into a solid. So to make that liquid slow down enough, to make those particles slow down enough so that they can stop moving around and be held in one spot, energy would need to be released from the molecules. Condensation and deposition are also phase changes that release energy. And then our phase diagram is going to kind of represent all these different phase changes and temperatures and pressures and how they're all related to each other. And there are a couple of specific spots on the phase diagram that I want to show you. And one of them right here is called the triple point. And the triple point is the point that represents the temperature and pressure at which all three phases of a substance can coexist. So if you have that specific temperature and pressure, you could have all three phases, and this one is for water, existing together at the same time, not changing from one to another. And then along this blue line, this is where you would convert from a liquid to a gas or from a gas to a liquid. And then along the red line would be from solid to liquid or liquid to solid. And you'll notice we have 2 points here called the normal freezing point and the normal boiling point. that term normal has to do with the pressure. The normal freezing point, as you can see, is at 0 degrees Celsius for water. That only happens at 1 atmosphere. Normal means at standard pressure, which is 1 atmosphere. Same thing with boiling. Water only boils at 100 degrees Celsius at 1 atmosphere. So if you change the pressure, as you can see, if you increase the pressure or if you decrease the pressure, the boiling point and the freezing point of water are going to change. Here are two other phase diagrams for things other than water. You can see for carbon dioxide, it's shifted up. So at our normal pressure, we're going to go directly from the solid to the gas phase. This is a phase diagram for carbon. You can see to turn graphite into diamond, you would need really high temperatures and pressures, which you have heard about how diamonds are formed in the earth. So those are kind of visually looking at all the different phases and transitioning from one to the other. Now, we also need to talk about how much energy is needed to make these changes of state. And we're going to use two new terms, the molar enthalpy of vaporization. And enthalpy is a fancy word for heat, so we're going to use those two interchangeably. And the molar heat of vaporization refers to the heat required to vaporize 1 mole of a liquid substance. And then the molar heat of fusion is the amount of heat required to melt 1 mole of a solid substance. And you can see here we represent heat of vaporization with a delta H, VAP. Okay, delta H is the symbol for enthalpy. Q is the symbol for heat. Q and delta H can be used interchangeably. Okay, so that's why you see that here. VAP for vaporization, and you'll notice the units of these numbers are kilojoules per mole. Okay, and then we have the heat of fusion, again in kilojoules per mole. So let's take a look at how we would use those particular heats of fusion and vaporization to do calculations with. So our question says, how much heat is required to melt 35.7 grams of solid methanol at its melting point? So our heat of fusion and heat of vaporization, those numbers are just conversion factors. So we're going to be doing conversions just like anything else. They are kilojoules per mole, so we're going to be using mole conversions like we've done in the past. So just like any other conversion problem, we're going to start with what we're given, 35.7 grams of methanol over 1. Okay. Now, we are talking about melting a solid, which is the heat of fusion, and if you take a look at the heat of fusion for methanol, it's 3.22 kilojoules per mole. Well, we don't have moles, we have grams, and we don't know the heat of fusion per gram. So what do we have to do to our grams? We have to convert it to moles. And how do you convert grams to moles? You use the molar mass. So from the periodic table, the molar mass of methanol is 3.042 grams per mole. The formula was in that table on the previous page. Now we can use our heat of fusion, which is 3.22 kilojoules per mole. So the moles cancel. We do the math. We get 3.59 kilojoules, and I kept 3 sig figs because of the mass that we started with up here. So make sure you know where that chart is. We're going to be using those heats of fusion and heats of vaporization to do calculations with in the next video. But all you have to remember is they're mole calculations just like anything else that we've seen.